Hi everybody, this is Mr. Folly who just dropped my magic pen. So let's get started. With titrations. All right, so mixing acids and bases, which are titrations. That always makes water and a salt. So a salt is an ionic compound. Okay, so here are four basic types of titrations that you're going to see. One, not that these numbers mean anything special, 1, 2, 3, and 4. But what I want to point out is this right here says strong acid because the pH is about 1. Okay, ending up here means that I'm dealing with a strong base. The pH is about 13. Okay, so if I look right here, see how this is clearly not 1. This would be a weak acid. And this is about 13. This would be a strong base. I know they're labeled, but if you're asked and try to figure out where they go, okay? So when you titrate acids and bases, you want to make sure you can explain why. So when I have a pH equal to 7, so if there's the point of inflection, concave up, changing my concavity. This is my point of inflection. So equivalence equals the point of inflection, and it also equals H positive concentration equals OH negative concentration. Okay. The other part that's super cool is halfway to equivalence is where pH equals pKa. So on this one, see how the equivalence is at 25? At 12.5, if I could read this well, that would be the pKa of that acid. Now, this is a strong acid, so strong acids don't really have pKa's. But if I took a weak one, here's a weak one. So if I took this one, and this is at 25, so at 12 it would be right here. If I could read it, that would give me my pKa. All right. Strong acid and strong base. Example, strong acid. Woohoo! Now, hopefully we remember what makes our acid strong and weak. So strong, 6 strong, group 1 and 2 hydroxides. We should consider this salt as Na positive and Cl negative. Okay, so strong acid and strong base, we said the pH is going to be 7. Okay, so neither will react with water. So let me show you what that means. Na positive, you think would react with water and make this. But remember how I said these are never allowed to happen because you can never make that strong base. So that means this reaction doesn't happen. So that means this reaction happens 0% of the time because this never forms. This is a strong acid. It never forms together. So it happens 0% of the time. Okay? So if I want to find the pH at a certain time, I find the limiting reactant in moles of excess. So if I'm at equivalence, XMV equals XMV. Remember, H2, X equals 2. If I have AlOH taken 3 times, X equals 3 for the hydroxide. Okay. If you have excess moles of hydroxide, that can be converted into OH negative, and then pH, and then POH, then pH. Okay, so it's just basically the pH runaround. So what is the pH when, make my pen a little bit skinnier. What is the pH when this much base reacts with this much acid? Note XMV does not equal XMV. So I'm going to do mole equals MV and have some fun with that. So moles equals MV, so it's going to be 0.5 molarity, 0.02 volume, 0.5 times 0.02. Whoops, I got to turn it on. Clear. 0.5 times 0.02 is 0.01. And that's moles of OH negative. And then the acid is going to be 0.25, again, molarity times volume, times 0.03. And that's going to be 0.25 times 0.03, 0.0075. And that's going to be moles of H positive. Okay, so these don't equal each other. So what I'm going to do is big minus small, 0.01 minus 0.0075 is 0.01 minus second answer, 0.0025 moles of OH negative remain. So if that's the case, what I'm going to do now is get that into a pH. Okay, so negative log of 0.0025 is going to be POH. Negative log, second answer, is 2.60. So then pH equals 14 minus 2.60, which would be 11.40. So that's a basic pH when I've got excess hydroxide. All right, weak acid, strong base. So weak acid, strong base. When I look at this, H2S, weak acid, strong base, there you go. I get Na positive, okay? Na will not react with water, so Na positive has no effect. But HS forms H2S. See how this is a weak guy? This is a weak acid, so that means it forms. So this very much happens, okay? So H2S is only 5% or so. So that means that this happens like 95% of the time. Woo, doggies. So that means I'm getting a lot of hydroxide. This makes the product basic. So this means the pH is greater than 7 at equivalence. Okay? So when I looked, no, it doesn't look like equivalence. When I looked up here, notice how we had to see where equivalence was. So this one, pH was above equivalence. And then on this one, pH was below equivalence. Okay. All right. So the other thing, so that's weak acid and strong base. So if I have strong acid and weak base, pH is acidic at equivalence because the conjugate acid of a weak base is powerful. Powerful. And that's kind of what I'm saying here for the flip. All right. To find pH at equivalence for weak and strong. Okay, so determine if it's at equivalence. Determine the moles of weak conjugate and total volume of solution. Do ice diagram of that molarity kickback. Ka times Kw, Kb equals Kw. Convert H positive to pH. So, woof, doggies, let's do it. Okay, that was very quick, but you'll see it. So I have ethylamine and perchloric acid. Okay, strong and then weak. Okay, so what I'm going to do is I'm going to figure out moles of each. So, calculate the pH equivalent. So, XMV equals XMV. Notice it's regular weak base, only one H. So I like to put my acid on my left. So I'm going to have 1 molar volume is what I'm going to solve for. And then I have 1 molar. It doesn't give me a volume. Calculate the pH equivalence points to titration of 1 molar ethylamine by 1 molar perchloric acid. So what I'm going to do is I'm going to say, because they'll be the same, I'm going to put it in 1 liter for easy math. Okay. So what's going to happen here first is C2H5NH2 plus HClO3 is going to, HCl4, pardon me, is going to turn into C2H5NH3 positive plus ClO4 negative. Now, because this comes from a strong acid, it's not going to kick back at all, okay? So what happens here, I'm going to do this first part in moles, okay? So I have 1 mole in 1 liter. So my initial ice diagram for this, when I think about it, I'm going to have 1 mole and 1 mole and 0 and 0. And the change is going to be minus all. It's a titration, minus all. It's a titration, plus all. It's a titration, plus all. It's a titration, 0, 0, 1, 1. Okay, so these are moles. Now what's got to happen is it's got to kick back. Okay, so this doesn't do anything. Okay, because it comes from a strong acid, so I've got to do a kickback with just this. C2H5NH3 plus H2O is going to give me C2H5NH2 plus H3O positive. So remember how this is a conjugate acid, right? It's got to act like an acid in the water. So now what I have to figure out is I've got 1 mole in 2 liters. Remember how I said 1 liter for easy math? So that's going to be 0.5. So I've got 0.500 minus, now it's weak, so it's not all. All right. So right now I've got to get my K value, pKb for this. Okay, darn it. So now I've got a lot of nonsense to do. So let me change my color into my nonsense color. Okay. So this is an acid, so I need to get this in acid terms. So pKb plus pKa equals 14. Okay. So that means my pKa is 10.75. So what that means is my Ka, so Ka is 10 to the negative 10.75. So pKb, so my pKa is that. Yep. Okay, so my Ka is second log negative 10.75. So that's going to be 1.78 e negative 11 equals, again, K expression. So I'm going to do these x squared products over reactants, 0.5 minus x. X equals, let's do a solver. Math, solver. No, clear. So I have parentheses, x squared, divided by parentheses, 0.5 minus x, close parentheses, minus 1.78 e negative 11, enter. Put in my guess point, 0.0001, alpha, enter. And x is, if I'm a fool, I put 2.98, but I'm no fool. Mama didn't raise any fool. I scroll all the way down and get e negative 6. Okay, and that is my concentration of H3O positive. Bum, bum, bum. So then if I want the pH of that, I'm going to have to negative log 2.98 e negative 6, and I'm going to get 5 point something. So second quit, negative log x, enter, 5.53. So far, so good. So you heard the bell ring, so I'm going to put you on pause, and we'll do that. Okay, so we got that one done. So find pH not at equivalence for a weak and a strong. So if we're not at equivalence, this one is actually easier. These are my favorites, okay? Determine the moles of each part, moles equals MV. Do ice in moles to find out what's left over, and then use this equation. This is the only equation that you want in your SOL that is not on the equation sheet. It's called the Henderson-Hasselbach equation. pH equals pKa plus log base over acid, where the base and acid are conjugates of each other. You can also use, yeah, this is brackets, so that means molarity. You can also use moles, okay? So we're going to do the ice in moles to find out what's left over. So here we go. 75 milliliter sample of 0.5 molar HCN is titrated with NaOH. So I hope this one will make sense to you. Remember how I don't believe in sodium? Plus OH negative will make our old friend H2O plus CN negative. Okay, so do you see how I have a weak acid and its conjugate? Okay, so I got to get moles of this. So 75 milliliters of 0.5 molar should be able to do that. 0.05 times 0.075 is 0.00375. So whenever we do titrations, we titrate in moles and do the kickback and molarity when we got to do that. So let's see here. There's moles. Oh, did I forget to? I think I forgot to change my volume. I'll talk about that later. 0.5. So we did moles. Yeah, 1 mole. Okay, I did it. I'm sorry. I hit the pause in the big middle part. And then this part is titrated with 0.454. Oh, man. What is the H positive in the solution after 3 milliliters of 0.054? So 0.454 times 0.003. 0.00132. 0.001362. 0. Now, because it's a titration, it's going to be minus all. Now, the all is going to be the smaller number. So I want to do minus all. So it's going to be minus 0.001362. And that's going to be minus all. And I just emphasize that. And this is going to be plus 0.001362. So in the end, at equilibrium, I'm going to have 0.00375 minus that answer, 0.002388. And this is going to be 0. 0.001362. Now I want to emphasize, remember how you can't really have zeros in here? So what would have to happen is some of this would kick back and do some weird equilibrium stuff. But this Henderson-Hasselbach equation, this man was a genius because he made life so much better for us. So pH equals pKa plus log base over acid. So my pH is going to equal, my Ka is this right here. So negative log of 6.2 E negative 10 plus the log of my base, see how this is the conjugate base, 0.001362 over the acid, 0.002388. And let's see what my calculator will say. Negative log 6.2 E negative 10, enter. I guess I'll chunk it into pieces. 9.208 plus log 0.001362 divided by 0.002380, close parentheses, and I get negative 0.242. Erase. So 9.208 plus the negative 0.242 is 8.96. So notice I have more acid, right? So that means I'm going to be a little more acidic than the pKa, and that's what I got. Oh man, what is the H positive in the system? So that means I've got to change this to H positive. So H3O positive equals 10 to the negative 8.96. So second log negative, second answer equals 1.08 E negative 9, 1.1 E negative 9. Woohoo! Titration of 200 milliliters of this and that, done for diprotic acid. Calculate the pH after this much has been added. Okay, so one thing I like that this is here. Do you see how I have a Ka equals 10 to the negative 5th and 10 to the negative 9th? The difference there is 4 powers of 10. That's 10,000 times more. So imagine if something had 10,000 times the impact. The other one doesn't matter. So I'm just going to get rid of it. Okay? So again, I'm looking at H2A plus OH negative. So H2A plus OH negative is going to turn into Ha negative plus H2O. So H2O, so this is 1 molar, 0.2 moles. And OH negative is, titration was done for this. Calculate the pH after 600 milliliters of 1.03 molar was added. So that's going to be 0.6 times 1.03. 0.618. Yeah. So notice, this is a whole bunch and this is a little. Okay. Now, because I've got this in here twice, I'm actually going to dump this one out. So the first thing that's going to happen is I'm going to end up with minus 0.2, minus 0.2, plus 0.2, 0. Don't care. So over here I'm going to have 0, 0.418, and 0.2. Now notice, this is going to react with this again. Oh, no. So what's going to happen is I'm now going to have Ha negative plus OH negative is going to give me H2O plus A negative. Okay, so my Ha negative is 0.2. My hydroxide negative is 0.418. This is 0. So I'm going to lose as much as I can, minus 0.2 again, minus 0.2 again, plus 0.2. So I get 0 I get 0.218, and I get 0.2. So now I'm going to use Henderson hasselbach, but I'm going to use the second pH. So pH equals, did it give me a pKa here? I'm sure they did. Ka2, which I scribbled out before I read the problem now. So I'm going to do the negative log of that right now. Negative log 3.1 E negative 9. So pH equals 8.51 plus log base over acid. Which one's my base? Okay, so in this one, I'm like, oh man, I totally messed this up too. Do you see how on this, I don't have a buffer system. I don't have a base and an acid. I just have hydroxide. So what that means is I have 0.218 moles of OH negative in 200 milliliters, 600 milliliters, and 0.8 liters. 0.218 divided by 0.8 equals 0.273 molar of OH negative. And is asked for pH? Calculate the pH. So what I'm going to do first is negative log 0.273 is going to give me POH. Negative log answer, and I get 0.564. So then the pH is 13.44. Please let it be there. 13.44. Surprised me on that one. That problem scared me for that, but we got it. All right, almost there. Partial titrations of weak acids and bases with a strong over-under equivalence point. That's what I just did. Woo! So weak acid with a strong base. Partial titrations make a significant amount of acid in conjugate base. This is called a buffer. This is a big deal right here. So my buffers are a big deal. Draw. It's not going to let me draw now. How do I know it's not going to let me draw? Oh, man. So my buffers are a big deal. So the two ways to make them is to have a significant amount of each one. So partial titrations make a significant amount of acids in conjugate base. So assume 1 liter of 1 molar HA is partially titrated with 1 liter of 0.5 molar NaOH. So titration's doing it in moles, right? 1 mole, half a mole, minus 0.5, minus 0.5, plus 0.5. Notice how I have the acid. I hope my pencil's showing up. And my conjugate base, so 0.5 and 0.5. Substantial amounts of acid in conjugate. Use a Henderson hasselbach, and we've got a mole. Okay, my mouse isn't working anymore, so I'm going to go ahead and make the assumption that this is going to die. So I'm going to stop it right here. It's been long enough, let's be honest. And I will say toodles to yoodles. Bye.